I feel very honored, privileged to be able to attend. I'm really grateful to be here. I love coming to Spain, and I love Big Data Spain. As far as my background, as Ruben was saying, I have led data science teams in industry for a number of years. For about a decade, I was leading data teams working on machine learning at scale. And also very early in terms of being one of the first few customers for Amazon AWS, working with cloud very early on, working with Hadoop, et cetera, very early on. So we were grateful to get into these technologies and learn from them and see them evolve. Over the past few years, I've been involved more with evangelism for large open source projects. As Ruben mentioned, with Mesos and then with Apache Spark. And over the past couple of years, I had the privilege of getting to help teach thousands of people in learning Apache Spark. From some of those experiences of teaching at scale, I've moved into O'Reilly and now lead the learning group at O'Reilly. We're responsible for all pedagogical aspects of O'Reilly Media, as well as all of the learning products and the studios. So I would like to bring some insights here from what we see out in the field, out in the use cases about data science. Where are the trends? Also some analysis that we've done, but also personal insights of where I see this heading in the near future. So I'll show some general patterns, some trends and analysis, and hopefully a few case studies, a few simple case studies of good examples of where I think data science is moving up into the use cases. Also, a little bit of a glimpse ahead of maybe some of the conceptual frameworks, if you will, of where this is leading over the next few years. The first off is about design patterns. So I like to think of system architecture in terms of patterns. I like to see where is the general kind of pattern that we're leveraging. Back in 2008, this is a diagram that I did for work. It's actually on a blog post on Blogger. There were a couple of executives at our company who were having an argument about whether or not we should be working in cloud. And they were discussing the different things that could run on cloud. So we came up with an illustration to show how we could be doing both batch analytics and real-time analytics based off of the current types of products. Some of them open source, some of them were proprietary, but again, this was 2008. So this was aspirational. We wished to have something like we have currently with, say, Spark and Kafka and others. Back then, we were just struggling to try to get this. I posted this on a blog article, and it became the top-ranked illustration on Google search for cloud architecture. And it stayed that way for a number of years. And it really showed that there was a lot of interest in this type of pattern for system architecture. People were very interested in seeing what kind of tools could realize this. So if I try to abstract a pattern, we see something much like this. There's data pipes, some type of data coming in, both batch and real time. There's some elastic compute component. There's some storage layer, also elastic, underneath that. Going off into use cases for analytics, probably some of the insights that you're surfacing go into search index so that you can retrieve them quickly. Underneath it, there's probably some type of container technology, some cluster scheduler, and cloud services under this. Now, this pattern here is interesting. I was a student intern at IBM Research 30 plus years ago. And at the time, on mainframes, we had almost all of these components. They were very expensive. You had to be a bank to use them. But we still had things like containers and cluster schedulers and all this in proprietary format. Over the past 30 years, though, open source has caught up. And so now we have very substantial open source projects that can provide these kinds of components. And they're fitting together well, and we're seeing large use cases. Maybe not all of them use the specific ones that I'm showing, but these are pretty good examples. Kafka, Spark, Cassandra, we see the three being used together very frequently. Also, underneath that, Docker, Mesos, on top of some type of cloud technology. Again, this is a very, very common pattern. Jupyter notebooks for analytics have become quite useful. And going off into search using Elastic and Solr, things like that. It may be that some of the components get switched out, but we see this kind of general pattern used over and over. Now, I pulled numbers this morning from Crunchbase, and the capitalization into these specific open source projects is interesting. It sums up to $588 million, mostly venture capital investment. What that says is that the Silicon Valley investor community believes that this type of pattern will be worth at least $10 billion within the next 2 years. I think that's very startling. And these people are making a big bet. They tend to bet pretty well. There are problems with this type of pattern, though. One thing is integration. I see that the different parts don't fit together as well as they could. Part of that, again, is driven by investors. If you go to Silicon Valley, and I'm part of a VC portfolio in Silicon Valley, Amplify Partners, but if you go there, they don't like to hear the word integration, not that much. It implies that you're giving up part of your market. So they try to drive companies to take over the whole market that they have, as opposed to collaborating together closely. That leaves a lot of room and opportunity for other companies to come in as system integrators, as experts, to provide that kind of integration. And most certainly, our hosts here, Paradigma and Stratio, are an excellent example of this. Customers need integration. And also up the stack, not just the plumbing, but into the data science use cases, how the data scientists will use this type of technology. That type of integration is also, I find, still somewhat lacking. So there's room ahead for improvement. Now, I also wanted to analyze real quickly, there's a number of different vendors who are trying to provide this type of pattern as a commercial service, as PaaS. So, just looking at it, definitely Databricks and DataStax are in that space. If you swap out the Cassandra part for, say, HBase, then Cloudera is definitely in that space. If you swap out a few other components, Hortonworks is definitely in that space. But also the cloud vendors. Definitely Amazon has big bets, looking at things like Kinesis and Spark, et cetera. Microsoft is there with Azure, also providing very interesting services. Google Cloud Platform, we'll hear much more about this from a friend who's speaking tomorrow. Very good bets in this space. They provide excellent technologies for this type of pattern. But also the big fish. IBM has moved in. They made big announcements about their investment in Spark. I was actually part of that announcement. And they're seeing a lot of opportunity for leveraging these types of technology. HP has Helion, and they're going after this kind of pattern. Dell recently acquired EMC, and clearly they're going after this as well. Ericsson, on and on. Samsung is making big investments. Alibaba, one of their divisions runs an 8,000 node Spark cluster all day, every day, the largest Spark cluster that we know about. Huawei is very big in this space, NTT Data, et cetera. What this tells me, though, is that the playing field is crowded. So with all these big fish coming in and trying to provide PaaS, there's probably going to be some type of consolidation. It's not really clear, but it does address a very large global market. So criticisms, my own opinion, I should say, is that there's a lot of emphasis on that type of pattern for the data engineering, not so much the data science. When you look at how Databricks, DataStax, et cetera, when they're making decisions about API, it's more from the engineering side. It's not from the machine learning side as much. That probably needs to change. Frankly, looking at data science teams, my experience has been that domain expertise trumps all. Knowing the nuances of banking or retail or telecom is much more important than the actual plumbing. And so I feel that domain expertise is the most critical part of data science. And maybe some of those open source vendors that I was showing earlier on in Silicon Valley, they don't quite get that. However, I think it may be changing. So I wanted to show 4 trends. Now, there's a lot of trends I could be showing, but for this time right now, going into 2016, I wanted to show 4 important trends that I've observed over recent period about data science. The first off has to do with leveraging contemporary hardware. So we have processors now with multi-core. We can build clusters with a large number of CPUs with not so many servers, really. Also, we have very large memory spaces. So again, we can build clusters that have a huge amount of resources. When you go back to some of the origins of relational database theory, go back to Edgar Codd and actually read that original paper from 1970. What Codd was talking about in terms of data banks and projections and all, it has a lot more in common with, say, something like Spark SQL than what we see from relational database management systems. I think that's very interesting. We're kind of back to the future in terms of how we leverage contemporary hardware. And so, as an example, out of Spark, working with data frames, working with Tungsten, the idea is that you can have a number of different language front ends. You can have SQL, R, Python, Scala, etc. But really, the abstraction is a data frame. A data frame allows you to do queries. The queries have logical plans, they have physical plans, they have a lot of optimization. You're leveraging the compilers to do code gen, you're doing column pruning, push down predicates, etc. Very sophisticated work on optimization. But then that also can drive how we handle the virtual machines underneath, JVM, or working with GPUs, working with LLVM, etc. So I think that this puts a lot of pressure on how we think about things like JVM, and the future is much more open to more optimization through things like Spark. I'll reference a talk here by Josh Rosen, who talks in much more detail about Tungsten, how really even a lot of the data structures in Spark are moving off heap to get away from garbage collection and do much more sophisticated things with the contemporary hardware, again, with the large memory spaces. That has huge implications on database management if you look into it deep enough. Trend number 2 has to do with generalized libraries. When we look at the kinds of applications built on things like Spark and Kafka and all the rest, we look at machine learning applications, there's a lot of custom work being done because we're not really fitting the data to the problem as well as we could. If we think about complex data sets that involve time series or geospatial or linked data or a number of different types of features and attributes, a general case for this would be to represent them as tensors. Tensors are difficult to use traditionally. It requires a lot of work on the programmer's part. So instead, we tend to take these complex data sets and fit them into matrices and then do work as matrices. That requires a lot of extra code, in my opinion. If it were possible to have a more general purpose tensor library, then we could get past this and stop writing as much custom code. The analogy would be looking 30 years ago, we used to write, prior to SQL, we used to write a lot of specific programs to do queries in COBOL to run against systems like IMS. And then when relational technology came out, we wrote less custom programs, just leveraging queries instead. I see a similar thing in machine learning. If we could represent the data as tensors and do factorization in a general case, we're going to write a lot less code or write it more efficiently. I had dinner a couple weeks ago with Anima and Anand Kumar at UC Irvine. She was working on this problem specifically using probabilistic methods to fit general case tensor representations into solvable ways based on top of Spark. And UC Irvine is working with Berkeley, working specifically with AmpLab to provide these kind of solutions eventually on top of Spark. Another person I'd reference would be David Gleich from Purdue and Stanford, similarly working with probabilistic methods to go after tensor types of problems. So definitely watch that space. I think that will be most interesting for machine learning. Trend number 3, workflows. Rather than thinking about APIs, I would encourage people to think more in terms of workflows. And workflows, by definition, include both people and technology. I've shown here a kind of generalized workflow diagram for a machine learning application. You start out and do some ETL, you do some data preparation. From there, probably explore the data. From there, you go into doing some feature engineering, prepare your training vectors, your test vectors for a machine learning algorithm. And then from there, you go and train models, you evaluate the models, and eventually move them out into use cases. What I'm trying to show in this diagram here is that the parts in red are hard. The parts in purple have to do with algorithms and APIs. They're not quite the hard parts. The hard parts have to do with exploring data expertly and understanding the domain. The hard parts include how to do feature engineering, and a friend of mine, Amparo, is going to be talking about feature engineering later here at Big Data Spain. You may be able to use things like deep learning to do some work on feature engineering. Similarly, we may see solutions coming up with symbolic regression and genetic programming. Again, that can do some feature engineering, but there's no magic bullet yet. Another hard part is evaluation. Machine learning comes from a number of different disciplines over several decades, and each one has its own language, its own mathematics, its own ways of evaluating. So if you're not careful about how you evaluate the results of modeling, you can get into a lot of trouble. So my point here is that we can actually create APIs and compiler techniques to handle a lot of the hard problems with machine learning, but there's a few parts that are still require a lot of human expertise. So think beyond the API, think about people and machines working together. The fourth thing has to do with looking forward, not just incremental changes, but what would be a next really big change. And for this, I'm going to embellish on the other points and point you toward what's happening in cognitive computing. In particular, I would reference Chris Ray, who is a computer science professor at Stanford. And also, he just recently won the MacArthur Genius Award, the MacArthur Fellowship, a very prestigious award in academia. There's a couple of talks that he's done at Strata conferences, our data science conference, and I highly recommend those. In particular, there's a project called Deep Dive, which is an implementation of a kind of cognitive computing. The idea is that you have probabilistic representation of both your data and your modeling together. And so it creates a kind of flywheel, if you will, where you can reason about the complex data, but you can also reason about the predictions and get a kind of feedback going on. This is an academic look at a number of different commercial types of AI that we see, such as Siri, such as IBM Watson, what's going on with Google now, Facebook has their own, et cetera. So Deep Dive is a very interesting look into these types of technologies. And again, it's very interesting how they can explore what they call dark data by having the best of both humans and machines working together. Okay, data scientists. I wanted to show a few points about data scientists. There's a lot of talk about how data science emerged around 2009, 2010. DJ Patil and Jeff Hammerbacher from Facebook, DJ Patil from LinkedIn, really helped to popularize this notion. But I want to go back to about 2001. William Cleveland out of AT&T, who was one of the people who helped develop what became R, he wrote a paper in 2001 about the need for data science curricula. And I would definitely recommend taking a look at that paper. It's really a lot of the original thinking about data science. And in the literature, it's the first mention that I see. So I would peg data science at 2001. In the same year, Leo Bremen at Berkeley, who was the inventor of random forest, he wrote a paper also critiquing the industry and seeing a kind of sea change where new types of machine learning and big data applications were coming online, Amazon, Google, et cetera, and made similar arguments. So 2001 is kind of when this field started, in my opinion. Rolling the clock up, though, again, 2009, 2010, it began to get popularized. We started having Strata conference at the same time. We launched that in 2010. So we've had 5 years of Strata now. And we also do a survey annually of the field to try to understand what are the trends, what are the tools, what are the salary distributions, et cetera. There was another report, though, that came out this year from RJ Metrics, actually came out this summer, and they had taken and scraped LinkedIn profiles, and they came up with an estimate of over 11,000 data scientists worldwide. I've looked at their methods. I'm not sure I believe this. I think it's a little overestimated. But even so, we are tracking a large number. So at O'Reilly, I've got linked here, and I will provide the slides. They're already up on SlideShare. I'll tweet about them later. But 2013 was interesting because we started to see people talking about how to get a data science job. People were still trying to figure out which tools to use. They weren't necessarily working with big data as much, per se, and they were also coding in scripts a lot. 2014, we started to see a much more rapid evolution of tools. You had to actually struggle to learn the tools and keep up with it. And so there began to be more of a correlation of tools and skills and how much money you would make in the field. And now 2015, we're starting to see a blurring between the divisions of open source and proprietary software actually being used together. So I'll point to the latest survey. Here's the 2015 one. And in particular, I give all credit to, by the way, to John King and Roger Magoulas, a couple of my colleagues who wrote this report. One of the things they did was to apply some machine learning to study machine learning. So we have some cluster analysis of people and tools out in the field. And out of that, we're seeing an interesting thing. Up at the top, the clusters there have Microsoft, also Tableau, Teradata, SAS, but also R. And so we've seen R shift over into more proprietary kinds of technology, even though it itself is open source. Another cluster down toward the bottom includes Spark, Hadoop, Hive, things like this, as well as the tools that come along with Python. So we're seeing more of an open source cluster down there. And then there are things like HANA, et cetera, where over off on its own, C++ types of implementations over off on their own as well. There's also some interesting insights in terms of how much people spend time working on different parts. So if you go back to the workflow diagram that I'd shown earlier, you can break it down into sections, and they've got some analysis here of how much people spend on each of those sections. And also, what kind of salaries do they earn based on how much they spend in each of those sections? I thought that was pretty interesting. Okay, so now I'd like to show a few use cases to try to show examples of what I mean about data science moving up into the verticals, moving up into the use cases. One that I'd like to highlight is in medicine. So I'm very glad to see that data science is moving away from the usual suspects of advertising, social networks, et cetera, where it's still very useful, but going out into much more real-world kinds of applications. Medicine in particular, I'd like to point to a company called Analytic, and Jeremy Howard is the CEO. He was formerly the CTO of Kaggle, the machine learning competitions. And his insight was there are decades of radiological records of people being treated for cancer. We have decades of this kind of data that we have to preserve. In the US, there are laws about preserving this kind of data, but it wasn't really being used. So he started to apply deep learning to radiological records for cancer diagnosis, going over decades worth of data. And they're using deep learning to help augment what the doctors are doing for treating cancer. The idea is it's like having a second opinion, except that by machine learning, we can have not just a second opinion, but a third and a fourth, 100 different second opinions from the machines so that the doctors have much more insights. And it's actually getting a lot of traction. Another area that I think is interesting is in politics. So this is a project out of Switzerland where they're taking a look at voting preferences. They're able to do some clustering on the voting preferences. And they surfaced pretty good predictive power. And it actually has some interesting, almost scary consequences, because what it means is that a given political candidate could go in and do some cluster analysis and come up with an optimized political platform so they could get the most votes possible. They wouldn't necessarily have to believe anything that they're doing. They could just use machine learning to find out where to win the election. And now that's in Switzerland, which is kind of a special case, but this talk here by Matthias Grossglasser is very, very interesting. Got to talk with him this summer some about it. So I think we're going to see some interesting things in the political arena with machine learning. Also, along with that, government ethics. Here's DJ Patil, formerly was leading data science at LinkedIn, and now he's the chief data scientist in the US, working at the White House, working closely with the Obama administration. There's a recent article that DJ had about what the White House is doing with data science. And about this, they're talking about opening up data. And clearly in the US, we see where government-sponsored open data is vital. Uber would not exist if it weren't for the fact that the US government were pushing out a lot of open data, especially for the maps. Similarly with weather and other things. So DJ is talking about being able to use data-driven analysis of, say, ethics from the White House level. And if that actually means that the White House is embracing ethics, then I think that's a great thing, finally. I'm not sure. I'll see what happens. Another area of use case I'd like to recommend is in sciences. There's a group called the Freeman Lab that's leading an effort called Code Neuro. They do neuroscience research essentially using lasers, microscopes based off of lasers where they don't hurt an animal, but they can observe neurons firing in an animal's brain while the animal is working on some complex task, like maybe working through a maze or going for food, things like that. And so they get enormous data rates watching tens of thousands of neurons activate in real time. And they use Spark to do some real-time analysis of these microscope telemetry, kind of like telescopes do. And they've created a lot of visualization, et cetera. But the fantastic thing that they've done with this is to put together a conference for neuroscientists where a few times a year, the top neuroscientists in the world get together for a hackathon. And they work with Spark, with Docker, with Jupyter Notebooks to do collaborative science based on these open source technologies. So there's some great examples under Code Neuro. I highly recommend taking a look at this. I think this is the future of repeatable science based on open source technology. Now, another use case that is very close to very near and dear to my heart is about learning. I'm much more responsible for learning types of data science these days. So I wanted to cover a little bit about that. And first off, how many people have used a MOOC? A lot of people have used a MOOC. Okay, awesome. So, there's a number of these: Coursera, Udacity, Udemy, edX, et cetera. There's a lot of MOOCs out there. Being somebody working in the field, I'm very curious about, after 8 years or 7 years of MOOCs, how well they're working. And so this is interesting. If you look at the first MOOC, it came from George Siemens and Stephen Downes in Canada. They were doing a social science course. Actually, very recently, George Siemens has published an article called Adios EdTech, Hola Something Else. The point being that he was very frustrated with the direction that MOOCs have gone. And he's very frustrated with the notion of EdTech in general. And frankly, so am I. When you look at analysis of MOOCs, here's an article that was in Nature magazine recently. It turns out that 80% of the students completing a MOOC already have an advanced degree in that field. And also 80% turn out to be within the richest 6% of the population worldwide. So the idea that MOOCs were going to democratize education is complete BS. It just has not panned out. And in fact, in the US, there are a number of universities that have actually rejected edX and no longer allow it because it's kind of a race to the bottom. And so I'll leave some analysis here of how that's going. There's a lot of criticism that MOOCs really missed the social dimension of education and that the kind of analytics that they went for dehumanized people. It made people parts of a system and then tried to optimize the system. So what else works better than MOOCs? If you haven't seen it before, there's a notion of something called an inverted classroom. You might hear this called a blended model or a flipped classroom. Khan Academy and others became kind of famous for doing this. Here's a nice, simple tutorial from UT Austin where they talk about how to flip a classroom. And it's really, you can think of almost like agile methodology from software engineering applied to learning. It's about how to iterate, how to make the most of the social interaction between the instructors, the TAs, and the learners. And it can be used online, and very effectively online. In particular, I would reference, there's a team up in Sweden. I spoke with some of them this summer. David Blackshafer is from Stanford. He's now at Uppsala. They have a very interesting project there called Scalable Learning, using an inverted classroom model. We're doing this also at O'Reilly. Another person I'd recommend, Philip Guo, is doing fantastic work with open source software for learning, particularly for computer science, where you can have visualization of data structures in real time and find out where it is that people get stuck when they're trying to solve a programming exercise. Very, very fascinating work, again, for more of this kind of inverted classroom model. If you take away just one slide from what I present today, that would be for Lorena Barba. Lorena Barba is from Chile. She's at George Washington University in Washington, D.C. now. She's one of the excellent critics about learning science, about the notion of quantified student, the notion of data-driven education, and just check out her talks. They're better than anything else I've linked here. But she's the real theorist that I'm looking at for guidance for a lot of what we're doing at O'Reilly. Because we don't really believe a lot of the ed tech arguments about quantifying students. Rather, we want to look at the social interactions between learners, between teachers and learners. If you haven't heard about it, one interesting area of data science that's being applied to education has to do with Jupyter Project. This is Fernando Perez out of Berkeley, also Brian Granger out of Cal Poly, and others. Really fascinating work to leverage notebooks, what was originally IPython notebooks, for education. And we're doing a lot of work with them directly. I see a number of universities and companies leveraging Jupyter, and I highly recommend checking that out. Here's actually an article about how we're using Jupyter, and the long and short is that we're able to take what would be an article or a chapter that has some source code examples in it. We take that and turn it into a Jupyter notebook, containerize it in Docker, and then run it on the cloud, so that we can have tens of thousands of people interacting with content as opposed to just reading it. And we're also working with ways to combine video along with the executable content. But again, using things like Mesos and Docker, et cetera, to achieve that kind of scale, and then instrument it to be able to have feedback loop based on data science of the social interaction. If you want to try this out, look at beta.o'reilly.com, and it has a number of examples from different professors and authors of using Jupyter notebooks for education, and you can go in and interact with the code, change some of the code, rerun it. It's a great feedback loop for learning. Now, in terms of learning and data science, I tried to come up with a grid representing some of the different things that we see in the world. And there's definitely the people who are learning on demand, asynchronously, and things like Pluralsight or Stack Overflow, they kind of address this. There's the blended courses, and maybe Caltech or UT or some of those are pretty good at that. There's the in-person things, like our conference here. So we're looking across the spectrum at O'Reilly how we can address different types of learning modes, and from it also be able to apply machine learning to help augment this. One thing I thought was interesting, this is from Julian Macaulay out of Stanford. They were able to apply machine learning to identify how people are learning about a particular group. He applied it to beer preference and how people learn about what kind of beer they like. He's from Australia and he likes beer a lot. But it's interesting because he was able to use computational linguistics, be able to use some text analytics, and then machine learning on top of that to be able to see how far away a person is from the community that they're trying to learn about or learn from, and how both of them are evolving, perhaps in different directions. So you can tell if a person is getting closer to the material or further away. That's a type of machine learning. If we can instrument the kind of classroom environments we have, we can help provide a lot more feedback. Another one that I'd recommend is from CMU, Anita Williams-Woolley, where she's looking at the group context. And in our work with conferences, we're seeing a big uptick in terms of companies sending teams to conferences for a specific reason, to learn a specific technology. And so we're trying to understand that, how we can adapt to more of a team context for training and for learning. One of the interesting things that Woolley provided, has been able to prove, is that if you have groups which maybe have one rock star component and then a bunch of other engineers, that's how Silicon Valley builds companies. But alternatively, if you were to take and have groups that have more balanced participation, actually more women involved is a critical factor. And also having a diversity of different formal backgrounds, that you can structure learning to be able to measure the group dynamic. And these types of groups outperform the rock star groups time after time. The one thing there about machine learning is to actually look at the discourse analytics, look at how groups are interacting while they're working on complex problems and trying to learn about them. So again, being able to use natural language processing and machine learning to give feedback in a learning context. Okay, so I'll finish up here with people and automation, which is where I see the long-term trend. When we do data science work, one of the things I've seen in the teams over and over is that we apply machine learning to a hard problem, maybe in advertising in my case, or social networks, We arrive at insights, we learn about them, and we get this kind of feedback loop between the people learning and the machine learning. Cognitive computing is pushing ahead on this and being able to go after more complex ways of cleaning up data and surfacing data, but again with that kind of feedback loop of people learning and machine learning together. And that's also a basic tenet of how workflows are designed in general. So I see some overlap there. The other thing that overlaps, it has to do with the gig economy. What we see with things such as Uber or Etsy, Upwork. I think Upwork is a really fascinating example of freelancers and a bid system for jobs versus freelancers. Who's the right talent to take the right job? Orchestra is something that's just come up recently for being able to do sort of microtask management, again, with this workflow concept of having some automation and some people involved. Uber, of course, uses this a lot. I think it's a very fascinating model how Uber is using machine learning in terms of pairing up drivers with people who need rides, optimizing routes, et cetera. So I think the gig economy thing is a very interesting area to watch how data science is evolving in 2016, again, because there's so much overlap. Orchestra is one. There was announcements about that earlier this morning where they've pushed a lot of this open source now. And again, the big idea there is that workflows include humans and machines. There's a conference coming up about this. Tim O'Reilly has a great article that he published on Medium just last month, or a couple of months ago. It's called Workers in a World of Continuous Partial Employment. And he makes a lot of arguments about where Uber is right now and TaskRabbit and others. They're not perfect. There's a lot of problems. There's a lot of social problems with them. But they're also addressing things that in the typical kinds of workplace, especially in the US, are not being addressed at all. So we're looking at this carefully and trying to get involved. There's also a conference coming up next month about this called Next Economy. And so for people plus automation, I feel that learning is key, and that's why I've gone in this direction, applying data science for learning at scale. There's excellent frameworks for this. If you've ever read Autopoiesis and Cognition by Umberto Maturana and Francisco Varela, it's a book that's decades old, but a really good insights about these kinds of systems, cognitive systems. So I would recommend that there is definitely theory leading us in this direction. So I'll leave that out there as a theme, hopefully tying together some of the points that you'll hear later in the conference. Systems of people plus automation learning together. And I think that that provides a kind of interesting duality for us to leverage. With that, I'll wish you a very good conference, and I look forward to all the talks. Gracias.